Oh, thank you very much. And thank you for inviting me. I never thought I'd be here at a South by Southwest conference, or whatever you call it, festival, as a speaker. You know, I can't play or write music. The only computer program I've ever written was a Microsoft DOS batch file. Some of you remember those. And the only movies I've ever made are of close relations. But here I am. It's wonderful. The kind of work I do is pretty far removed from anything that's immediately useful or profitable. It is pursuing an ancient goal. The goal is to try to understand nature in simple, general, and unified terms. By unified, I don't mean that we won't have separate physicists and chemists and biologists. We all have our own techniques for learning things, and I think this will go on forever. But we have an image of, at the deepest level, when we keep asking why, we come to a set of fundamental principles that govern everything. One set of laws of nature to rule them all. And this is what we're aiming for. How do we know that we'll ever get there? We don't know, but the historical progress of science has been all in that direction. I think the first great step toward unification was taken by Isaac Newton in unifying the celestial and the terrestrial. You know, it had been thought, particularly by Aristotle and his followers, that there were entirely separate sets of laws for things in the heavens at the orbit of the moon and beyond, and things here on Earth. In the heavens, there is no change except for motion, and the motion is natural motion in circles around the center of the Earth. Here, below the orbit of the moon, our dull sublunary lives, motion change is endemic, things are always changing, and natural motion is toward the center of the Earth if you're talking about earth or water, or away from the center of the Earth, directly away if you're talking about air and fire. Everything else is unnatural. It was Isaac Newton who, for the first time, applied a set of laws that to both the celestial and the terrestrial. To be specific, this is when he was at home after the plague had reached Cambridge University, where he had been working. He realized that the moon, traveling around the Earth, is always bending its orbit toward the Earth. It's not flying off in a straight line, so that in effect, it's accelerating toward the Earth center. Likewise, an apple falling to the ground in Lincolnshire, where he lived, is accelerating toward the Earth's center. The moon's acceleration is 3,600 times smaller than the apple's acceleration, not because they obey different laws of nature, but as Newton realized, it's simply that the moon is 60 times further from the center of the Earth than an apple, and hence the acceleration is 60 square times smaller. And this same analysis, he then showed, applies to the planets and to the moons of Jupiter and Saturn. That all had to do with gravity. Newton knew very well, and he expresses this very forcibly in his book, The Optics, that there are other forces in nature beside gravity. They remain rather mysterious. Electricity was known, magnetism was known. They were thought to be rather separate phenomena. Then in the 19th century, the work of Ørsted in Denmark, Ampere in Paris, and Faraday in London, showed that in fact there is a deep relation between electricity and magnetism, a relation that was finally spelled out in detail by James Clerk Maxwell. Among other things, a changing magnetic field produces an electric field. That's what allows you to generate electricity, by the way. And a changing magnetic field produces an electric field. Excuse me, a changing electric field produces a magnetic field, something Maxwell discovered, so that you can have changing electric and magnetic fields supporting each other in space without anything else around. And Maxwell calculated the speed at which that disturbance would travel through space and found, lo and behold, it was the same as the speed of light that had been measured. And in fact, as Maxwell realized, that's what light is. It's a self-sustaining oscillation of electric and magnetic fields, so that the textbooks had to be rewritten. Electricity and magnetism is not a separate subject from optics. They're the same subject. Well, physics and chemistry, though, were still quite separate. And the evidence for that comes from a strange phenomenon. At the end of the 19th century, a number of physicists declared that physics is just about finished. The only thing we have left to do is to push our measurements to the next decimal place, get a little bit more accurate. In a sense, they were right, but for physics, they were thinking of electricity, magnetism, light, heat, motion. None of them realized that physics could hardly be finished because it had not yet succeeded in explaining the phenomena of chemistry. They would not have thought that that was part of their job description. You know, why does sodium and chlorine form a stable chemical compound, salt? If you ask a physicist that, he would direct you to the next building on the university campus where the chemists sit. But in fact, it was realized through the understanding of what an atom is and through the development of a new kind of physics known as quantum mechanics, it was realized in the 1920s that atoms are just a positively charged nucleus surrounded by electrons, and when different atoms get together in a molecule, the molecule is held together by the electric forces, already very well understood, between the electrons and the nuclei. And you could calculate, using the principles of physics, the energy it takes to rip apart a molecule of salt or to decide whether a different chemical compound is stable or not stable. So that chemistry became part of physics. Chemists hate it when I say that, but it is true. That's all just physical science, only a small part of the world we live in. What about life? What about biology? The first great step was taken by Darwin, not so much in realizing that evolution had occurred, because fossils were known. Many biologists, zoologists, botanists realized that there had been something like evolution going on. Even Darwin's grandfather, for that matter, had known this. But it had generally been thought that evolution, the gradual improvement in species, occurs because of fundamental biological principles, different from anything in physics or chemistry, that drives life toward betterment. What Darwin did was to point out that that assumption is unnecessary, that given inheritable variations, inevitably evolution will occur toward organisms that are more fit to survive and reproduce. One of the great ideas in all of science. But the mechanism for inheritable variation was completely unknown. Darwin had no idea what it was and didn't try to guess. It was discovered in the 20th century with the working out of the structure of a chemical molecule, DNA. and that was in the 1950s. Increasingly today, biology requires, for its deepest level of understanding, chemistry, which in turn requires physics for its deepest level of understanding. Now, there things stayed for a while. In the 1930s, it became known that atomic nuclei consist of particles called protons and neutrons, and there was another step of unification, I suppose. It was realized that these particles undergo reactions. For example, there are reactions in which protons turn into neutrons, and these reactions are evidenced in kinds of radioactivity and they produce the heat of the stars. The first step in the chain of nuclear reactions in the sun, is just such a reaction where protons are turning into neutrons. So again, it was another step toward unification of things we know about in our laboratory with the greater world beyond the orbit of the moon. But things were very messy. I mean, we're talking about physical principles which are supposed to be at the bottom of everything, and yet the principles themselves seem like a mess. When I started graduate school, it was in the 20th century. I won't tell you when. There were 4 kinds of force known. Electromagnetism, well, that was well in hand. And in the 1940s, we learned how to deal with electromagnetism in the context of quantum mechanics. There were strong nuclear forces, the forces that hold protons and neutrons together inside atomic nuclei, that, for example, hold 92 protons together in the uranium nucleus, even though those protons are all repelling each other electrically, all having the same charge. And we now know that these strong nuclear forces not only keep the protons and neutrons together inside the nucleus, they keep the quarks together inside the protons and neutrons. More fundamental particles. We didn't know that when I started. In addition to the strong nuclear forces, which are much stronger than electromagnetism, there's another class of nuclear forces called weak nuclear forces, which are much weaker, as you might guess. They don't hold anything together, but they are what allow neutrons and protons to turn into each other, as I mentioned earlier, and allow the sun to shine. We had a good theory we had no theory at all for the strong forces, and we just didn't know what they were or how to calculate anything about them. We had a good interim theory, a practical back of the envelope theory for the weak nuclear forces. We could calculate some things, like the rate of a certain nuclear decay, radioactive decay, but there were a lot of other things that when we tried to calculate, we got nonsense. We got answers like infinity, even if we're calculating something perfectly sensible, like a probability or an energy. And so we knew we didn't have a decent theory of these forces. And then there was a fourth force, the first one that was known, but in some ways the most mysterious, and I'll come back to it, the force of gravity. How can you bring unity to this kind of mess? Well, one thing we could do was to play with the idea that there was some kind of simplicity in the equations. For example, we guessed, and this is true, a lot of people made this guess in the course of the 50s and the 60s, that there was a particle that carried the weak nuclear force in the same way that the particle of light, the photon, carries the electromagnetic force. When 2 charged particles interact, they interact by exchanging a photon. Similarly, the weak nuclear force may occur because when a neutron turns into a proton, a force-carrying particle comes out and produces the particles that are produced in this kind of radioactivity, electrons and neutrinos. This particle was called the W particle. W stands for weak, not Weinberg. And there were obvious problems with this. The W and the photon had the same spin. That is, these particles are actually spinning on their axes around the direction of their motion. And the amount of spin was the same. It's a spin equal to 1 in what physicists like to call natural units. So they look similar, and that accounted for some of the properties of the known properties of the weak interactions. But there was an obvious discrepancy. The W particle was so heavy it hadn't been discovered yet, and we all speculated about it, but said, well, it's just too heavy, our accelerators aren't good enough, we have to go to the public for more money and build bigger accelerators. The photon is massless. How can you put these entirely different things together? How can you unify weak interactions carried by the W particle and electromagnetic interactions carried by the photon? An idea was hatched around 1960, originally by a theorist named Yoichiro Nambu, working in Chicago, inspired by similar problems that occur in the physics of magnets and superconductors, and then picked up and made much more general by Jeffrey Goldstone, a young theorist, I think then at Cambridge, and improved on in 1964 by a bunch of theorists. Their names are Brouden-Anglais, Peter Higgs, and Guralnick, Hagen, and Kibble. The idea, going back to Goldstone and Nambu, is that it is possible for the equations of physics to be very simple, and for example, to have two particles like the electron and the neutrino that appear different because the electron has a mass and the neutrino doesn't, yet appear in the equations in exactly the same way. And nevertheless, the solutions of the equations, which describe the actual phenomena we observe, don't have that simplicity, that unification. The technical term we use for it is symmetry. We call this a broken symmetry. A typical example is what happens in a permanent magnet, and this is one of the things that inspired Goldstone and Nambu. In a magnet, the laws that govern the iron atoms are completely indifferent to the direction of your observations. I mean, it doesn't matter whether you're looking at the magnet from the north, the south, the east, the west, above, below. The laws that govern the forces between the iron atoms and the magnet look the same from whatever point of view you observe a bar of iron. And indeed, when you take a hot bar of iron, hotter than 770 degrees centigrade, the iron does look the same in all directions. There's no preferred direction. However, as the iron cools, a magnetic field appears. That points in a particular direction. It appears spontaneously. It breaks the symmetry between different directions, and all the iron atoms line up so that they're spinning around the same axis as defined by the magnetic field. That's a classic example of a broken symmetry. But in particle physics, we weren't looking for symmetries that would we weren't looking for a way of breaking the symmetry between different directions in space. We were looking for something that broke the symmetry between, say, electrons and neutrinos, or W particles and photons. The first theory that did this, or I should say probably the first successful theory that did this, was developed in 1967 by me and independently in 1968 by my dear friend, the late Abdus Salam, with the purpose of unifying the weak and the electromagnetic fields. In order to break the symmetry between, say, the W and the Z, we introduced not a magnetic field, of course, that wasn't what we were trying to accomplish, but we introduced a set of fields that don't have any sense of direction in ordinary space, so that they're not pointing north or east or anything, but they do have a sense of direction in the kind of internal space which distinguishes the different types of particle, and would break the symmetry and, for example, allow the electron to have a mass when the neutrino wouldn't, even though they appear the same way in the equations. This kind of field is called a scalar field. The word scalar simply means it doesn't care about direction in space, in ordinary space. We found we had to introduce, in order for mathematical consistency, to introduce 4 scalar fields. And 3 of these serve the purpose of giving mass to the positive W, the negative W, and a new particle which was required by the theory, a neutral particle that carried a new kind of weak force called the neutral current force, and I call this new particle the Z. And these particles were all subsequently discovered in the 1983 experiments at CERN. The 4 scalar fields we introduced, 3 of them just serve to give mass to the W plus, the W minus, and the Z. The 4th one is left over as a kind of debris from the symmetry breaking, and it is observable in principle as an actual physical particle. One of the characteristics of this particle is, because it's a knot of energy and momentum in a scalar field, it has no spin. It's like, you know, this year the Cy Young Award went to a pitcher of a knuckleball. A knuckleball is, I don't know how he does it, but it's a way of pitching a ball so it has no spin, and therefore travels an erratic path, makes it very hard to hit, which is why this guy won the Cy Young Award. This particle is not known as the knuckleball particle, unfortunately. It's known as the Higgs boson. In my 1967 paper, the first reference of these earlier papers from 1964 was Higgs, and well, we needed a short name for it. The theory of Salam and me predicted all the properties of this particle except its mass and its name. So we didn't know how heavy it would be. There were various indirect signs. It couldn't be much heavier than 100 times the mass of a proton, and, excuse me, 1,000 times the mass of a proton. And we thought we could build accelerators that could produce this particle. Such an accelerator was built, called the Large Hadron Collider. It is at CERN in Europe. The accelerator runs under the Jura Mountains on the border between France and Switzerland. And it did succeed last July in producing this particle. We now know that it exists and it weighs 133 proton masses, something we were not able to predict. We don't yet know that it is the predicted Higgs particle. One of the things that has to be checked is that it is a knuckleball, that it's not spinning, and that hasn't been done yet. The accelerator is right now shut down because they're trying to increase the energy, and that takes a while, I think maybe for 2 years. But I believe that at the end of the 2-year period, experiments will start up again and will, in fact, confirm what most people already believe, that this is the the last missing particle in the electroweak theory, the theory that unifies the weak and the electromagnetic forces. Oh, I'm not that bad. Good. Meanwhile, the strong nuclear forces have been understood. That's a whole other story which I played a minor role in, but other people played a much more important part. The theory of the strong nuclear forces looks very much like the theory of electromagnetism and the weak nuclear forces. They, again, are transmitted by particles with a funny name, gluons, but these are particles quite similar to the photon. They have the same spin, equal to 1 in natural units, and they have 0 mass. We don't see them for a complicated reason. As you try to pull them apart, the force between them increases, and you can never get them pulled apart. But they are the particles that produce the forces that hold the quarks together inside the protons and the neutrons. Now, this is all very nice, but it's certainly not the end of the story. I mean, there are things that are left out of this picture. Astronomers tell us that 5/6 of the mass of the universe is something that has to be attributed to a particle different from any particle allowed by the Standard Model. Oh, I'm sorry, I should explain. The Standard Model is a name I gave to this combination of the strong nuclear force theory and the electroweak theory. Put together, that's what's called the Standard Model. The Standard Model doesn't account for dark matter, and there's an even more mysterious dark energy, an energy inherent in space itself, which can only be detected because it appears that it is causing the expansion of the universe to speed up, to accelerate. And it makes up about 3/4 of the total energy of the universe. In other words, much more than all the matter, including the dark matter. Well, 3 times, in fact. Even apart from the things which are not described by the Standard Model, evidently it's far from unified. For one thing, we have strong forces which are much stronger than the electroweak forces, and that's not explained yet by any kind of spontaneous symmetry breaking. There is a strong hint that we're getting from a number of different sources that a unification, also including gravitation, may be possible, but that the simplicity which unites the strong, weak electromagnetic and gravitational forces will only be seen in the phenomena when we go to much higher energy. Well, that's always the excuse. I mean, wait until we go to higher energy. Unfortunately, in this case, when I say higher energy, I mean 10,000 trillion times higher than any energy that can be reached in the laboratory. And that's not just a lot of zeros strung together. I really mean 10,000 trillion. There are at least 3 reasons for this. One is the problem I already mentioned about the unification of the strong and the electroweak forces. Those forces depend slightly, very slowly, on energy. The strength of the strong nuclear force decreases as the logarithm of the energy increases. It's inversely proportional to the logarithm of the energy. And logarithms, as you undoubtedly know, change very slowly as you change what they're the logarithms of. And apparently, and this is a calculation that was first done with 2 coworkers, Howard Georgi and Helen Quinn and me, back in 1974, I think. If you plot the strength of the strong nuclear force as it depends on energy, and also the weak and the electromagnetic, which also depends somewhat on energy, they all seem to come together. And although 2 curves typically will come together unless they don't, but for 3 curves to come together at the same point tells you something is going on. And they all seem to come together at this energy, 10,000 trillion, what is it? 10,000 trillion times the energies that we can study in the laboratory now. Another hint is the fact that although I said earlier neutrinos have zero mass, they don't really have zero mass. They have a very tiny mass, about a millionth of the mass of an electron. This is just, it was first discovered as an effect when we observed neutrinos coming from the sun. They didn't seem to come in the right way that we expected. And this is just the mass level that we would expect from some fundamental symmetry breaking occurring at an energy of 10,000 trillion times what we observe. The final clue is gravity. Gravity is incredibly weak on the scale of laboratory physics. Even in a molecule, no one has ever detected the gravitational force between two nuclei in the same molecule. It's so weak. It's many, many trillion times weaker than the electric forces. But gravity is produced by energy, whether it's energy in a mass or any other kind of energy. And if you go up to sufficiently high energy, the force of gravity becomes as strong as any of the other forces. What energy do you have to, for example, if you have two particles with the same electric charge as an electron, how heavy do they have to be for the gravitational attraction to be just as strong as the electrical repulsion? Well, the answer is 10,000 trillion times heavier than the particles we know about. I'm being careless with a power of 10, but not that much, not more than 1. Now that's an intriguing picture, although in a way very discouraging. For one thing, it presents us with a puzzle. I mentioned that everything about the Higgs boson, Higgs particle, was predicted by the electroweak theory except its mass. Its mass, in fact, that's because its mass, in fact, sets the scale of all the other masses of the quarks and the electron and so on. So it's, in a sense, the fundamental unit of mass for the elementary particles. Well, as a fundamental unit of mass, shouldn't it be up there 10,000 trillion times higher than the energies we're used to? But it's down at a level of 133 proton masses where we can actually observe the thing. Why? It's true they had to build an accelerator that cost $10 billion before they could produce the Higgs boson because it weighs 133 proton masses. But from a different point of view, from maybe a more fundamental, if less fiscal point of view, why is the Higgs boson so light? 10,000 trillion times lighter than all the other fundamental mass units that we know about. I don't know, it's a mystery. What we need, evidently, is more data. Because we theorists have been looking at these problems. Sure, we didn't know the mass of the Higgs boson, but we certainly knew it was less than 1,000 proton masses, which by these standards is also incredibly light. So we've been looking at these problems for a long time, not just since last July, and we haven't made progress. Some theorists have tried developing entirely new approaches called string theory. I think they're probably doing the best that can be done, but they're not getting anywhere. They're not producing any predictions that can be compared with observation, and they haven't really come up with any one theory that shows how the four forces are unified. What we need to give us a kick in the pants and inspire us to theoretical ideas that will get us to the next step of unification is more data. Newton benefited from centuries of observations of the planets. People looking up in the sky, in those days the sky was darker than it is now, and seeing 5 things that look like stars but moving in an irregular way across the zodiac. Darwin benefited from the fact that England was filled with clergymen who in their spare time were naturalists and dug up fossils. We need data, and unfortunately, it's very expensive. As I said, the Large Hadron Collider, although I don't know an exact figure, probably cost something in the neighborhood of $10 billion, which is a lot of money. On the other hand, it's not a lot of money when compared with something else that we've been doing that is related to science, supposedly, and that is manned spaceflight. It's an interesting comparison between the International Space Station and the Large Hadron Collider. The International Space Station has so far cost about $100 billion, 10 times what the Large Hadron Collider cost, and has produced nothing of scientific interest. I'll be glad to defend that if anyone wants to argue. I say this, I don't know why I'm dragging, yes, I do know why I'm dragging this in. I'm dragging this in because of something that happened here in Texas in 1993. We were at that time working on a large accelerator of our own called the Superconducting Super Collider, which would have been placed in Ellis County. Well, it was very big. Ellis County would have been in it. And it would have accelerated particles to 3 times the maximum energy that will eventually be reached at the Large Hadron Collider. It would have discovered the Higgs particle 15 years ago and would be now doing a much, much better job than the LHC can do in probing its properties and looking for new things, like maybe the particle that makes up dark matter. And these two projects were both seen as Texas projects. The SSC obviously would have been in Texas, and the International Space Station, although it's up there, would be monitored from the Johnson Manned Space Flight Center in Houston. And they came into competition in Congress. The Clinton administration said, well, we're in favor of both, but we're really in favor of the International Space Station. And Congress just barely passed the International Space Station and voted down the Superconducting Super Collider, something which has left me permanently scarred. Funds now are drying up even more than back in the early 90s. We all read the newspapers about this. What can we do about this? Well, this is a democracy, and it seems to me we don't have the right to expect the public to support this search for a unified view of nature unless we can get them interested in it. And that's why I'm here. Thank you. Thank you. Well, I think I finished on time. We have time for 10 or 15 minutes of questions. I think yeah, go ahead.
Recently in the news, there was a discovery of a black hole which spins near the speed of light. I'm just wondering, does that evaporate faster because of that phenomenon or not?
I think the answer is yes, it probably does, but I'm not an expert on black holes, and I remember a time in my life when, although I knew the theory of black holes, I didn't believe they actually existed, and now it's clear they do, but I have never. So I think you're right, but I don't know for sure.
So let me ask the leading question.
Oh, well, yeah, that is a good question. Thank you for asking it. I think there are a number of things that can be done on a fairly small scale. For example, there's an experiment that would produce neutrinos at Fermilab near Chicago. They would travel under the Earth to a mine in Minnesota where they could then be detected. That way we would learn about the properties of the neutrinos, this tiny mass that I mentioned, and the way that mass correlates with the way they interact. I mean, we describe neutrinos in two different ways. There are electron neutrinos, for example, which produce electrons when they hit something, but they don't have a definite mass. The neutrinos that have definite mass are mixtures of the neutrinos that interact in definite ways. We need to sort that out because, as I mentioned, neutrino masses are one of our few tangible clues to something that's going on at this incredible energy of 10,000 trillion times the energies we can study. There are other things like looking for the decay of the proton. The proton is usually thought to be absolutely stable. Experiments so far show that protons live longer than a million years. That's much longer than the age of the universe. So you're not going to observe a proton decay by just having one proton and waiting for it to decay. But that's an average lifetime. If you have a million protons, which isn't that hard, 1,000 tons of water, then maybe you'll see one decay a year. That is very difficult because there are cosmic rays that can imitate proton decays, but these experiments have pretty well dried up. Also, I should say, the experiment to look at neutrinos traveling hundreds of miles under the Earth and then being detected in a mine in Minnesota, that also hasn't been funded. So there are lots of things. These are not at the multi-billion-dollar level. They're sort of at the $100 million level. It's not money you can come by easily, but it's not in the same category as a big accelerator. I think after the LHC is finished, we will need another accelerator, very likely a collider which collides electrons and anti-electrons, because that produces something very clean where we understand the theory very well. In the Large Hadron Collider, you have two protons colliding with each other. Protons are bags of quarks and gluons. It's like two garbage trucks colliding. And all sorts of garbage comes out, and you have to be very clever in looking for the thing you're interested in, the Higgs boson or the dark matter particle or whatever it is. You can do things much more precisely with electron-positron colliders, but that's very expensive. That's also at the multi-billion-dollar level. Most people think it would have to be an international collaboration. In fact, there's even a name for this, the International Linear Collider. And they have workshops on it and so on. But one of the things I went through with the Super Collider was trying to get international collaboration in building it. And that isn't easy because it's only going to be in one country. And other countries don't want to put money into any country but their own. So this is going to be very, very difficult. There are lots of things that we need to do in space. You have this James Webb Space Telescope. That appears to be going ahead. You have this exhibition here. And that will, as was mentioned earlier, that will supplant the Hubble Space Telescope and get us much closer to the origin of stars, for instance. But there are other things that need to be done. For instance, the universe is filled with microwave radiation, left over from the time when the universe was, when the current Big Bang was 380,000 years old. I won't say the universe was that old. The universe may be eternal. But the Big Bang in its present version was 380,000 years old. At that point, the universe became transparent to microwave radiation, and the microwave radiation that was filling the universe, well, then it wasn't microwave radiation, then it was visible. Now it's been redshifted to microwave frequencies. It's filling the universe. We've been studying it, and it's taught us a tremendous amount about what was going on in the early universe. But there are other studies that need to be made, which we haven't yet seen how to do, how to get the money for. In particular, looking for traces of gravitational waves. They leave an imprint on this microwave background. So that's another thing that needs to be done. And I suppose, you know, people in biology have things they'd like to do. I'm not against that. Loop quantum gravity. Oh, that's what you're referring to. Yeah. Well, you used the word emergence, right? Was that the word, emergence? Yeah, okay. This came up a lot in arguments about the supercollider. Some people who work on the physics of ordinary matter, so-called condensed matter, liquids, solids, pointed out that in their work they don't really use much of elementary particle physics. They use principles that emerge when you have very large numbers of particles, like a million particles in a gram of water. You have concepts like temperature and entropy, which make no sense on the level of a single molecule of water, but which do make sense when you have a million particles all together. And they said, therefore, there's no sense in which what you're trying to do for much more money than we spend is more fundamental than what we do. My answer is there's no question that whether it's condensed matter physicists or biologists or philosophers use concepts that are not directly related to elementary particles and don't get much help from elementary particle physics. Yet the principles on which they base their work do emerge. They emerge in the sense that they are logical consequences of the physics that we study, the elementary particle physicists study. The fact that then the details of elementary particles aren't important to someone who studies superconductivity or tidal waves or whatever is beside the point. The point is not to try to reorganize the way science is done. I explicitly, in fact, said I don't want to do that and couldn't if I wanted to. The point is to understand why things are the way they are. And if you want to understand why water boils at a certain temperature, you have to trace a chain of reasoning back to something very fundamental, and that very fundamental level is the level of the elementary particles.
Hi, first of all, thank you for coming today. This is fantastic. If we consider the amazing amount of knowledge that's been gained in the 20th century and in the 13 years past that, do you think that we'll see as much knowledge being discovered in the next 113 years, or are the tools to do that just too expensive?
I'm scared. I'm scared that the tools may be too expensive. We'll see what comes out of the Large Hadron Collider and out of the Planck satellite, which I believe on March 21st we'll have a news conference where and they're studying the microwave radiation, and they may have some exciting news about the microwave radiation. We'll see. I mean, it's certainly too early to despair. But I think, you know, despair is a distinct possibility. The idea of atoms goes back to about 400 BC, to Leucippus and Democritus, and they speculated that all matter is composed of atoms traveling in a void. And it took a long time to verify that. It took until about 1900 before chemists and physicists were convinced that atoms were real. There were physicists, in fact, even in 1900, who still didn't believe in the existence of atoms. And we may be in for another 2,500-year hiatus. I certainly hope not, but that's more of a problem for you than it is for me.
Right. Hello, and thanks again for talking. It was tremendously informative. It's kind of implicit in the way you were going with this, but you've obviously had a lot of academic success, so I'm kind of curious. How do you feel about open access for scientific journals? Good, is it bad? What kind of, if you could wave your magic wand, what would you guys have?
Well, that's a question much closer to the interactive South by Southwest concerns. I have mixed feelings. We have an open access system, at least in my kind of physics. When you write a physics article, so often before you send it to a journal, you post it to a website called Archive, and every physicist in the world can read it. And in fact, it works very well because they can often then tell you what's wrong with it and you can correct it before it gets published. I do think that the journals play an important part, not in editing articles. I have never seen an article in physics exposed to serious editing, the kind you get when you submit an article, say, to the New York Review of Books, where they actually make it better. What they do is they make sure that you're using their style for footnotes. That's the kind of editing that goes on. So I don't put any value on the editing that the journals do, but they do a very good job of sending out the articles to experts, and they know who the experts are, and getting rational assessments of the articles and then judging what they should do. Should they accept it? Should they turn it down? And so on. I would hate to give that up. Now, I know that some open access journals do that, but I don't know how well they do it. And, I have a kind of Edmund Burke's feeling that when you have existing institutions that are working pretty well, you don't scrap them for something else which sounds like it'd be a little better. And so we have these journals like the Physical Review in my field that I think work very well. They're so expensive these days, only libraries buy them. But they represent a permanent form of publication which, on paper with ink, that I find very reassuring, that an article of mine will still be there gathering dust on the shelves a century from now. I think, I've overstayed my welcome, and thank you very much. You've been a wonderful audience.